Now we come to module 3 of chapter 7. In this module, we shall study some properties of Laplace transform and summarize them in form of some theorems. First is convolution of Laplace transform. Before going to the convolution theorem, first we define what is Laplace convolution integral. The Laplace convolution integral of two functions ft and gt defined in the interval 0 to infinity is defined as f star g t equal to the integral from 0 to t f t minus x gx dx. This is the convolution of two functions f and g. Next comes some properties of Laplace convolution integral. Now it is trivial to show that the Laplace convolution integral satisfies the following properties. First property is that commutative property, that means f star g t is equal to g star f t. Also, if c is a constant, then f star cg is equal to cf star g, and that is equal to c of f star g. Third property is associative property, that is f star g star k is equal to f star g star k. All these properties can be proved from the definition of the convolution. Now we come to convolution theorem. It states that if capital Fp and Gp are Laplace transforms of two functions defined in the interval 0 to infinity, then the inverse Laplace transform of the product capital Fp into capital Gp is the Laplace convolution of the functions f small ft and small gt. That is, Laplace inverse of capital F into capital G is equal to the convolution of small f and small g. This we have to prove. For proof, we start with the function capital Fp into capital Gp. Capital Fp is the Laplace transform of small ft and capital Gp is the Laplace transform of small gt. So, we write them as integral fx e to the power minus px dx into integral 0 to infinity gy e to the power minus py dy. That can be written as double integral from 0 to infinity e to the power minus p x plus y into fx into gy dx dy. Now we substitute x plus y equal to t in this integral. Now keeping y fixed in the x integral, if we make this substitution, then we have capital Fp into Gp equal to this integral, equal to integral from 0 to infinity, integral from y to infinity e to the power minus pt f of t minus y gy dt dy. Now we interchange the order of integration so that t integral is the outer integral now and y integral is the inner integral, and we get integral from 0 to infinity e to the power minus pt dt, that is the outer integral, and inner integral becomes integral from 0 to t f of t minus y gy dy. Now the inner integral is the convolution of small f and small g, so that we can write this as integral from 0 to infinity e to the power minus pt f star g t dt, and this is the, according to definition of Laplace transform, is the Laplace transform of the convolution function f star g. So, that is equal to Laplace transform of f star g. So, we get from here capital Fp into capital Gp is equal to the Laplace transform of f star g. So, taking Laplace inverse, we find that Laplace inverse of capital F into capital G gives the convolution of two functions small f and small g, that is defined as integral from 0 to t f of t minus y gy dy. We shall now use this convolution theorem to find the Laplace inverse of p by p square plus a square whole square. Here we choose capital Fp as p by p square plus a square, and we know that this is the Laplace transform of cos at. That means capital Fp is the Laplace transform of cos at, and we choose capital Gp as 1 by p square plus a square, and which is the Laplace transform of sin at by a. So, that the given function is the product of capital Fp and capital Gp. Thus, using the convolution theorem, we can write Laplace inverse of capital Fp into capital Gp, that will give the convolution of the function small ft and small gt, where small ft is cos at and small gt is sin at by a, and their convolution is given by integral from 0 to t cos a t minus y sin ay by a dy. That is equal to, after some simplification, 1 by twice a integral from 0 to t sin a to y minus t plus sin a t dy, which can be evaluated, and that gives 1 by twice a into minus cos a to y minus t by twice a y equal to 0 to t plus t sin a t, which can be simplified to give t sin a t by twice a. So, we have learnt what is called the convolution of two functions, and we have seen through convolution theorem that Laplace inverse of the product of Laplace transform gives back the convolution of the two functions. Now, we shall study another property of Laplace transform, and this property will be summarized through Tiberian theorems. Now, we shall learn Tiberian theorems. Through this theorem, we shall see that the behavior of a function ft in the neighborhood of origin in some sense is reflected in the behavior of its Laplace transform as mod p tends to infinity. That means behavior of ft as t tends to 0 is reflected in some sense in the behavior of capital Fp, which is the Laplace transform of small ft, as mod p tends to infinity. First theorem is the initial value theorem. It states that if ft is a piecewise continuous function in the interval 0 to infinity and is of exponential order, that is of order e to the power ct, then its Laplace transform capital Fp satisfies limit mod p tends to infinity p capital Fp is equal to limit t tends to 0 plus small ft, and that is equal to f of 0. For proof, we start with the function p capital Fp. This is equal to 0 to infinity integral p ft e to the power minus pt dt. We integrate this by parts and we get minus e to the power minus pt ft t from 0 and infinity plus integral from 0 to infinity e to the power minus pt f dash t dt. Now the first function vanishes as t tends to infinity, so that it gives f0 plus integral from 0 to infinity e to the power minus pt f dash t dt. Now if we make mod p tends to infinity, we find limit mod p tends to infinity p capital Fp, this is equal to small f at 0 plus limit mod p tends to infinity integral from 0 to infinity e to the power minus pt f dash t dt, so that the second term vanishes and we get limit mod p tends to infinity p capital Fp equal to small f at 0. We may remark here that we have assumed Laplace transform of f dash t exists, which obviously tends to 0 as mod p tends to infinity. So we have proved the initial value theorem. The next theorem is the final value theorem. It states that if small ft is piecewise continuous and is of exponential order, that is ft is of order e to the power ct, then its Laplace transform satisfies limit mod p tends to 0 p capital Fp equal to limit t tends to infinity small ft. For proof, we start with the left hand side, that is limit p tends to 0 p capital Fp equal to limit p tends to 0 p into integral from 0 to infinity e to the power minus pt ft dt. Here we have substituted the value of capital Fp, which is the Laplace transform of small ft. Now we integrate by parts, so that we get limit p tends to 0 minus e to the power minus pt ft t from 0 and infinity plus integral from 0 to infinity e to the power minus pt f dash t dt. Now if we make limit p tends to 0 and noting that the first term here it vanishes as t tends to infinity, we get making p tends to 0 as f0 plus integral from 0 to infinity f dash t dt. Now the second integral can be evaluated and we get limit p tends to 0 p capital Fp as limit t tends to infinity small f t. So this proves the final value theorem. Now we shall find out the Laplace transform of the Ci function, which is defined as integral from infinity to t cos u by u du for t greater than 0. For this, we take small ft equal to cit. Then f dash t is equal to cos t by t. So that from here we get t f dash t equal to cos t. So if we take Laplace transform on both sides of this equation, then we find that Laplace transform of t f dash t is equal to Laplace transform of cos t. Now, Laplace of transform of cos t, we know that it is equal to p by p square plus 1. So that right hand side becomes equal to p by p square plus 1, and left hand side we know from the properties of Laplace transform, this is equal to minus ddp of integral 0 to infinity e to the power minus pt f dash t dt. And this leads to, after integrating by parts this integral, we get minus ddp of minus f0 plus p capital Fp. Here capital Fp is the Laplace transform of small ft. So we find minus ddp of minus f0 plus p capital Fp is equal to p by p square plus 1. Hence, from this expression after integration, we find pfp is given by minus half log 1 plus p square plus constant, where c is a constant. Now, from the initial value theorem which we have learned, we know that limit p tends to 0, p of capital Fp, this is equal to limit t tends to infinity small ft. And from we have taken small ft as Ci function, which is the definition of Ci function, we know that as t tends to infinity, ft is equal to 0. So we get by initial value theorem, limit p tends to 0, p capital Fp equal to limit t tends to infinity small ft, and that is equal to 0. Using this condition, we find that small c equal to 0, and hence capital Fp is given by minus 1 by 2p log 1 plus p square. Next theorem is known as Watson's lemma. This states that if small ft defined in the interval 0 to infinity is of exponential order, that is ft is of order e to the power ct, and if ft is equal to summation n equal to 0 to infinity an by n factorial into t to the power n mod t less than capital R, then capital Fp is equal to Laplace transform of small ft has the asymptote series capital Fp given by summation n equal to 0 to infinity an by p to the power n plus 1 as mod p tends to infinity. This result can be proved formally by applying Laplace transform to the expansion of ft term by term, and that will give Laplace transform of small ft is given by capital Fp, and if we take the Laplace transform of this function, then we get this series as p tends to infinity. So, this proves the result. So, in this module, we have studied some important properties of Laplace transform in form of convolution theorem and in form of Tiberian theorem, and applied these theorems to find Laplace transform of some functions. With this, we conclude module 3 of chapter 7.